in ecology, one thing that we're often interested in is how a population is distributed in their environment. And so, interestingly, when we look at the natural world, we typically see three very common types of distributions in the natural world. These are clumped, uniform, and random distributions. So the most common is clumped. If we look at our screen at the left-hand side of the screen, we see a clumped distribution of cattails. And so, not surprisingly, cattails, which require a great deal of soil moisture in order to survive, are typically found in very localized areas. As you drive down the road and look at the passing scenery, you'll see cattails only in areas that are low-lying and that have a good deal of moisture around them. As you come into Wilmore, if you look at that gas station there close to the Y, there's some cattails growing in a ditch just below that gas station. And so, interestingly, that's just an area where enough moisture accumulates during a greater part of the year, and that's sufficient to allow these cattails to grow. And so, if you look at other organisms, then this tends to be the case. Organisms typically exist in this clumped distribution, and that's simply because, similar to the cattails, the suitable habitat is only found in certain areas, and so animals tend to display this clumped distribution as well. They tend to be found in areas where habitat is suitable. If you go out and look at a farm, or you go out on Asbury's property, for instance, then you'll find animals. You'd find rabbits, for instance, concentrated not down in the woods, but in the grown-up areas, not in mowed fields either, but in areas that fields that have been allowed to grow up, and you have some blackberries and brush that's starting to become quite thick, and so you find rabbits that are quite thick in those areas at fairly high concentrations, and not deep in the forest or up in the cleared fields. Alright, we also have a uniform distribution that's more rare but sometimes observed in nature. And so our example that we have of a uniform distribution on the screen is interesting. It's penguins. These are penguins that are nesting. And so these penguins are sitting on eggs. And this is a uniform distribution because the penguins don't let, the female penguins don't let another penguin get too close to them. They drive the other penguin away, and so you end up with this uniform distribution with an equal spacing found between the individuals. You also find uniform distributions in places like the desert, where you have plants growing, and the distributions are uniform there because water is so limiting that it only allows one plant per certain amount of area. If another plant tries to grow in that area, it will die because all the water is being used up by the plant that's already present there. And so uniform distributions are typically observed where resources are limited and competition for those resources is extremely competitive. Random distributions are sometimes observed, and so random distributions are observed in situations like what we see in the right-hand side of the screen. We have these evergreen trees out in the western U.S. That fall, and there's plenty of soil moisture, there's plenty of light, and so where they fall, they're able to grow. We typically see random distributions where resources are abundant and the organisms can grow, or in the case of animals, move wherever they like without having to be concerned about running out of food. We talk about some predators. Interestingly, the big hairy spiders that you see, wolf spiders, display a random distribution. They're predators and they wander from place to place seeking prey, and typically they're distributed randomly because there's lots of insects. There's no shortage of insects, and their prey are found almost everywhere, and so wolf spiders also are found almost everywhere. We want to talk a little bit at this point about population growth. This is a topic that's relevant to both animal and human populations. If we look at the screen, we see the history of the world in terms of the number of people present on the planet for the past several thousand years. You'll be interested to note that it's not until just the past couple hundred years that the population of the Earth has started to really grow exponentially. And so close to 2,000 years ago, there were 250 million people on the face of the Earth, and so of course now we have more people than that just here in North America. And then look at how the population spikes up. 1800, 1 billion, 1930, 2 billion, 1970, 4 billion, 1999, 6 billion, 2007, 6.6 billion, and then we passed 7 billion, as you might recall, in, was that October of 2011, if I am remembering correctly? But we are over 7 billion at this particular point. They picked out a baby in Indonesia and called it the 7 billionth person on the face of the earth, and gave it a balloon. But there are over 7 billion people now on the face of the earth. And so human population has displayed something that we officially call exponential growth. Exponential growth is a type of growth that occurs when the growth of a population speeds up as the population gets bigger and bigger and bigger. And exponential growth, as we'll see, also occurs in the natural world, but exponential growth never lasts forever. So historically, let's illustrate exponential growth here. So historically, the population growth rate has been low. The growth rate was about 0.1% per year about 2,000 years ago. But by 1750, the growth rate was about 2% per year. And so as the populations get larger and larger, then the rate of increase in the population gets larger and larger. And so it's a simple idea. If you have 10 animals and they double, you end up with 20. But if you have 1 million animals and they double, you end up with 2 million. And then when those double, 4 million and 8 million. And so you're going up faster and faster and faster because your reproductive base is getting larger and larger. It's interesting to note, this slide's just slightly outdated, 6.6 billion. There are now 7 billion people on the face of the earth. But at that time, we were adding 77 million people per year. It's also interesting to note, if we look at this graph from our text, we see that, where is most of this growth occurring? And most of the growth is occurring in these so-called less developed countries. This is a term that's now used in place of the term third world countries. And so these are the countries that can least afford this growth. But interestingly, and perhaps sadly, certainly sadly, that in terms of the fact that people lack resources there, this is where most of that growth is occurring. The growth in more developed countries is much less than what we see in these less developed countries. And there's all sorts of questions, and it's certainly beyond the scope of our class to discuss why that is. Why is it that growth rate is higher in less developed countries versus more developed countries? But what we do want to mention is that something typically occurs as a country becomes developed that we refer to as a demographic transition. And so this boils down to what I'm going to describe now. Before the Industrial Revolution, in all countries, both birth and death rates were high. Lots of people were born, and many of those people did not survive. Remember, we didn't have antibiotics at this time. We didn't have health care that was what it is today. And, I know there's lots of controversy about health care today, but let's be honest, 200 years ago, we didn't have anesthesia, we didn't have antibiotics, we were struggling with the germ theory of disease. We didn't know that a doctor shouldn't touch his hand to his boots and get dirt on his hands and then perform surgery. That's literally what was happening in the Civil War. So, I use the term healthcare loosely. What I mean is we were very primitive in our understanding of anything regarding human health, and so lots of people died, unfortunately, as a result of that. We had this high birth rate and high death rate. But as countries become industrialized, and as our understanding of medicine has improved, our sanitation has improved. We don't dump human feces out into the streets anymore. We don't have wells that are contaminated with human feces. That's a situation that used to cause outbreaks of cholera that killed thousands of people in concentrated cities, even here in North America, a couple hundred or less years ago. Then death rates decrease. And so for a short period of time, you have this high birth rate and you have a lower death rate, and so you have a very rapid population increase. But then what we've always observed is this. This is all depicted by our screen here. So we start out with high birth rate and high death rate. And here we've just described this particular occurrence. And so the death rate drops for the reasons we just mentioned, but birth rate remains high. But then fascinatingly, we also see that the birth rate eventually drops. And so in a developed country, we see we have a low birth rate and a low death rate. So not many people are born, but most of those survive. Now, the question becomes, so if we look at the world today, we see that most of the growth in the world is coming from the less developed countries. And so they are either out here on the left-hand side or they are here in this demographic transition. Now, admittedly, the death rate is unfortunately, tragically, very high in some of these countries. But in other countries, the death rate is somewhat lower because of the at least pseudo-availability of antibiotics and medical care. And so the growth rate is quite high in these countries. And so the question becomes, is the birth rate eventually going to drop in these countries as they become developed? And it's an interesting question. Now, there's all sorts of controversy about how many people this world can hold. Can this world hold 6 billion? Have we already increased the carrying capacity of the Earth? Can it hold 7 billion? Can it hold 10 billion? That's a question that remains to be answered. Humans are different than the animals we'll talk about during the course of our chapter because we actually have the ability to modify our environment and increase our carrying capacity by increasing our technology and our ability to produce food and resources. And so genetically modified organisms are actually a big part of that and may aid greatly in the production of food to especially the impoverished parts of the world. But everyone agrees that there is a carrying capacity to the Earth. Eventually we'll run out of space. And so the question really becomes, what's going to happen in these less developed countries? As they become developed, is that birth rate going to drop as we've always seen previously, or is it going to remain high? If it remains high, then it may be problematic. If it drops, then perhaps everything will be okay as a result of the fact that the population of the world will stabilize. They're interesting questions, very complex questions, and involve lots of sociology topics that aren't part of our class. But certainly the ecology, the population growth aspect, and the resources that are available aspect is a part of our class, and a very interesting topic, and one that we should be aware of as we move forward in our lives. Here's an example. In Germany, I don't have the year, I'm sorry that this was taken, but this is in the past decade. And so in Germany, the average income is $31,900. The population growth rate is 0. It's not growing at all. People are replacing themselves, but no more than that. And almost everyone, as you would expect, is literate. Female literacy rate is 99%. In Yemen, the average income is $1,000 a year. The female literacy rate is 30%. 70% of females cannot read. And the population growth rate is 3.5%. I'm not going to attempt, and it's not appropriate to in our biology class, to go into why this is, but I'm simply presenting this as an observation. This is what we observe in the world today, and we've always observed this demographic transition that's taken place previously, and so the question becomes, is that going to occur in the future in these less developed countries? And if that'll have a big impact then on the future of the human population on the Earth, as you certainly realize. Alright, so we all agree as far as the Earth goes that there is a limit to how many people the Earth can support. Populations can grow exponentially for a while, but they always hit this thing that we refer to as carrying capacity, this line here. So we have population size on the y-axis, we have time on the x-axis, here we have exponential growth, but eventually as the curve levels off, we refer to this as logistic growth. Here's exponential growth, here's logistic growth. And logistic growth is the process of that growth rate leveling off to remain consistent with the carrying capacity of the environment. And so typically the population fluctuates above and below that carrying capacity once the population grows to a certain size. And we observe this in all cases in the environment. If you put bacteria into a little test tube, then you'll observe this in those bacteria. And of course the biggest question is what's going to happen to the Earth in terms of the number of people on the Earth. Eventually we will hit that carrying capacity, but no one knows exactly what that is. So what limits population growth? Human population growth and animal population growth. And we divide the limits to population growth into two different categories: density-dependent and density-independent factors. Density-dependent factors are factors that increase with population size, and density-independent factors are not influenced by population numbers. And so density-dependent factors include things like running out of food, increased ease of disease transmission, increased waste levels that may also relate to transmission of disease. These things cause a decrease in birth rate, an increase in death rate because animals are starving to death, or they are transmitting disease from one organism to another, or perhaps both. And so density-dependent factors become more pronounced as the population grows. Density-independent factors are not influenced by population numbers at all. So natural disasters, droughts, extreme temperatures, all these things fall under the heading of density-independent factors. Here's Mount St. Helens in Washington State in the United States. And so this is a great example of a density-independent factor. And so this was a volcano that exploded, as you may realize, in the early 1980s. These are people. That's one man, that's another man, maybe that's a man sitting down, I'm not sure. But look at those trees. And so those trees were just blown over by the eruption of that volcano. And so certainly the populations of animals that were present in this area were killed. Whether there was one or whether there was 1,000, the animals in that area would be killed. So it was a density-independent factor that controlled those populations. We want to now talk briefly about age structure of population. And so when we look at a particular population, we can tell a lot about whether the population is growing, shrinking, or remaining the same as a result of examining the age structure. And so when we look at these populations here on the bottom of our screen, we see that the organisms in these categories are divided up into both male, shown on the left-hand side, that's the symbol for male, and female on the right-hand side. And then we have pre-reproductive ages, reproductive ages, and post-reproductive ages. And so in a growing population, the pre-reproductive ages then outnumber the reproductive ages. And so this would be a population that's growing. As these individuals move up, the wider this is, the more individuals present. As these individuals move up, that means the population is actually expanding. Here we have a population that's remaining constant. And it's so simply the pre-reproductive ages are replacing the reproductive ages, and everything remains constant there. It doesn't grow or shrink. Here we have a population that's actually shrinking. The reproductive ages are less in number than the pre-reproductive age individuals are less than the reproductive age individuals, and so this population will eventually shrink. So as you would expect, what we see in the various countries, this is taken from our text, but interestingly, I'm not sure why they chose South Africa being one of the more developed countries on the continent, but in any case, we still see this trend. In South Africa, we see a growing population, and in the United States, we see a stable population. It shouldn't be shrinking quite at this point, but it is fairly stable. Some of the European populations are shrinking just a bit. We want to now talk about a very interesting topic in ecology, and that is the topic of survivorship curves. So animals employ different strategies to reproduce and to replace themselves in the environment. And we can categorize these animals based on how many of them are alive at any particular point in the lifespan. And we break these down into what we refer to as type 1, type 2, and type 3 survivorship curves. In a type 1 survivorship curve, we have animals that reproduce, and they produce, type 1 animals produce very few offspring, and they provide a lot of parental care. I really don't like that our book used grass as an example here. And it does fit, but we're just less familiar with the biology of grass. And so let's use mammals as an example. Let's talk about elephants. Elephants have a 2-year gestation period. They don't reproduce until they're quite old, and they produce one calf at a time, and they provide a lot of parental care. You wouldn't want to mess with a baby elephant. and they nurse that elephant and protect it for a long period of time. And so this means that if you look at the overall survival rate of elephants, like here's the percent of lifespan of an elephant's down here. Here's 100%. How old do elephants get? Maybe 50, 60 years old at the oldest. I'm not quite sure, actually. But if that's the case, then that would be 100% of their lifespan. And so if you look at, say, elephants that are out at 80% of their lifespan, most of the elephants are alive. Here's number of survivors on the y-axis, and here's percent of lifespan on the x-axis. Most of the survivors are alive at almost the end of the lifespan, so very few die until the end. And so that's how elephants approach reproduction, and how all mammals and large animals reproduce and approach replacing themselves in the environment. Now let's contrast that with a type 3 survivorship curve. In a type 3 survivorship curve, we have an animal that produces a ton of offspring. A mosquito would be an example. Mosquitoes produce a tremendous number of offspring, and most of those are going to die. Most of those are not going to make it to adulthood. Or we could talk about fish. Like if we talk about a big carp, a large carp that might be 3 feet long. That's a fish that we find here in North America as a result of introductions in almost every body of water. Well, that fish, when we look at how many offspring it produces, it may produce 1 million offspring in a year, but 99% of those are going to die. So if we look at the number of survivors very early on in life, we see that it's quite low. Most of those animals die before they get to even 25% of their lifespan. But if they make it to 25%, then death is pretty steady after that. So once a carp gets to be, say, 6 inches long, then not too many things are going to eat it. But when carp are hatched, they're the size of a mosquito larvae. They're tiny. You'd almost need a microscope to see them. So all kinds of things eat them. Crayfish, fish, insects eat them. And so that's a type 3 survivorship curve. If you're a type 3 survivorship organism, your strategy is to produce a huge number of offspring, throw them out into the environment, and hope that just a couple survive. So there's a type 1 versus type 3 survivorship curves. Type 2 survivorship curves are intermediate. And so here, death is unrelated to age. These are typically intermediate-sized organisms like a lizard, or you may see lots of lizards this time of year. Even this is western lizard, but in central Kentucky we see skinks and fence lizards. And the same thing would apply to sparrows, songbirds, rabbits. These are organisms that are prey for lots of different predators. So they produce a fair number of offspring. They provide some parental care in some cases, not in the case of lizards, but in the case of rabbits and birds. And so some die when they're little, some die when they're intermediate age because they're eaten by other organisms, and then some survive to the very end of their lifespan. And so type 2 survivorship curve organisms are in the center there between type 1 and type 3. This is an important concept, though. This is not something unique to our text. This is one of the classical ideas in ecology, that there are different strategies by which organisms replace themselves in the environment. You can produce a few organisms and invest a lot of care in those, making sure that they survive, and that's what type 1 survivorship curve organisms do. Or you can produce a ton of organisms, provide no parental care, and hope that a few survive, which is what type 3 survivorship curve organisms do. Alright, and so as we talked about earlier, when we talked about the human population, then we see that there's a lot of uncertainty regarding the future of the human population. So here we have a projection that is given to us by the United Nations, and there are 3 different actual projections here. So in the low growth rate projection, by 2050, we end up with just a few more people than we have now, a little over 7 billion. Medium growth rate, about 8.5 billion. And high growth rate, we end up with 10 billion. And so growth rates now are about 1.2%, and it's unclear what's going to happen in the future. And as we pointed out previously, most of that uncertainty revolves around the uncertainty of what's going to occur in those developing countries. It is clear, though, that no population can undergo exponential growth for an extended period of time. So we know that, but here's an interesting example of that. This is a natural experiment that took place in an island off the coast of Alaska. And this was an island that had no reindeer on it originally, but some reindeer were introduced. Just about 15 reindeer were introduced back in the early 1900s. And interestingly, that little group of reindeer grew up to about 2,000, over 2,000. Those numbers are a little off. So it was about 2,000 reindeer that were present on the island in around 1940. And then, because of resource depletion, specifically they ringed the trees. They ate the bark in a circle around the trees because they had nothing else to eat and all the trees died. They suddenly ran out of resources and there was this huge population crash. And so what we see on the screen is oftentimes what we observe in the natural environment, and of course what we want to avoid here on the face of the earth. But we all agree that there are limits to population growth, and eventually density-dependent factors do limit the growth of populations.